The topic for today's topic is about the work, energy, and power. So first, we always start with a definition. How we define the work. The definition of the work, it is the product of force and displacement. When we take a product of force and displacement, we get another quantity and a physical quantity, and that physical quantity is known as a work. So example, there's an object, experience a force of 3 newtons, and we move the object to a distance of 2 meters on the horizontal surface. So what is the work here? As we know, the work is a product of force and displacement. So in this case, the work will be the force into displacement. The force is equal to 3 and the displacement is 2. So 3 multiplied by 2, we got 6 Newton meter. Because the unit of the force is newtons and the unit of distance is meter. So that is Newton meter, and Newton meter is also known as joules. So I can say the work is 6 joules. Even though the force is a vector quantity, displacement is also a vector quantity, but work is not a vector quantity. Why a work is not a vector quantity? The main reason for a work not to be a vector quantity, because it does not follow the vector addition rule. The vector addition rules are not applicable on the work, like the triangle and the rectangle or a parallelogram method. That's why work done is classified as a scalar quantity. So we don't have to mention a direction because it is a scalar quantity. So whenever we move an object horizontal on the horizontal plane and we want to calculate a work, so the work is actually a product of force which we applied and the displacement. But whenever you calculate the work, you always take the force and the displacement in the same direction. Let's take an object is there, which is experiencing a force F, and it was making an angle theta with a horizontal. So this force will have the two components. For those who just joined the session now, our topic for today is work, energy, and power. And I started with the definition of a work, which is a product of force and displacement. Say there's an object, experience a force F, which is making angle theta with a horizontal, and the object move horizontally a distance of 2 meters or a distance d. Now, if you want to calculate a work in this example, how to calculate a work? Work is a product of force and displacement, but we always take the force and the displacement in the same direction. So this force is making or having an angle with x-axis or horizontal. So this force will have the component, one of the component of a force is with an angle and another one is opposite to the angle. So the component of the force which is with an angle, that is F cosine theta, and the component of the force which is opposite to the angle, that is F sine theta. So which component I should use to calculate the work here? Is it F cosine theta or F sine theta? The force is having a components, horizontal and the vertical. The horizontal is F cosine and the vertical is F sine. So which component I should use when I'm calculating? So we always take the component of the force. No, we don't have to take both. We will only take the one which is parallel to the same as the direction of the force, like same as the direction of a displacement or opposite to the direction of displacement. So in this case, what component we will take? We'll take F cosine theta. So when I calculate a work in this example, the work will be F cosine theta times D. So idea is that whenever you want to calculate a work, how to work out the work done, it's the force and the distance. It's the force and the distance should be in the same direction or opposite direction. Because sometimes we have to calculate a work done against the resistive force. So in that case, the direction of the force will be opposite to the direction of the motion. So yeah, I will repeat for those students joined just now. We started the concept of a work, which is a product of, we started with a concept of a work, which is a product of force and displacement. And work is a scalar quantity, it's not a vector quantity because it is not having a direction or it does not follow the vector addition rule. So if I want to calculate a work, say there's an object, experience a force F, and it was making angle theta with x-axis. So, and the object move certain distance. When it experiences a force, it move a certain distance. So this will have two components. The force will have the components, always a component which is with an angle that is cosine. So this will be F cosine, and the component which is opposite to the angle will be F sine. If I want to calculate a work, the work is a product of force and displacement. We always take the component like the force and displacement which are parallel to each other. So which component is parallel to displacement? Like this is F cosine theta and this one is a displacement. So I want to calculate a work. I will use F cosine theta times T. That will be the work. Is it clear, this one? Anyone having a doubt or a question till this point about the work? If you want to calculate a work, and say this is an object which is experiencing a force F, and the object is moved horizontally, distance D, and we have the angle with y-axis. The theta is there with y-axis. So what we have to do whenever a force is, because the force and the distance here are not parallel to each other. So what we have to do, we have to resolve the force into the components. So one of the component of the force is with an angle. So what is this component? This will be F cosine theta. And the other component which is parallel, that is equals to F sine theta. So we have two components, F cosine theta and F sine theta. Now I want to calculate a work. Work is a product of force and displacement. We always take the component of the force which is parallel to displacement. In this example, which component I should use? Is it F cosine theta or F sine theta? Which component I should use to calculate a work? Yeah, that's right. It will be F sine theta times D. So whenever you want to calculate a work, remember one thing, that the force and the distance, you always take them parallel components. Okay? Let's take another example. An object is there of weight W, and you moved on the inclined surface. The length of this inclined surface is example D, and the height which you move, that is H. And we want to calculate how much work is done to move this object on the inclined surface. We want to calculate the work done on inclined surface. So to calculate a work done, I need the force and I need the distance. Or the displacement, you can say. So which component of the force I should take? Because the weight is a force of gravity, so we'll take weight here. But what about the distance? Should I take D or H? If I want to calculate a work, which component I should take? Is it D or H? To calculate a work, should I take D or H? So whenever, as I mentioned, whenever we calculate a work, we always take the parallel components, the component of the force and the displacement, which are parallel. So in this case, the force is a weight here. So weight is a force. So which component we should take? So we should take H, because H and W are parallel to each other. So when I calculate a work done, I will calculate the work done will be weight multiplied by height. Is it clear, this example? But what if I will use a force F? There was a force F, and now I want to calculate a work. So if I want to calculate a work by the force F, so in that case, if I want to calculate a work, so how it should be? If the force F is there, then the distance which is parallel to the force F is D. So in that case, I will use the work will be F multiplied by D. If I was having the weight, then I will multiply it by height to calculate the work done. And work done does not depends on the route or the path we follow. So if I use a formula weight multiplied by height, or I use the formula force multiplied by distance, I will get the same answer. So work done does not depends on the route or the path we follow. Like a simple example, an object is there on the ground, and you want to lift this object to a certain height above the ground, like you want to place on the shelves. The three different paths you follow. This is path A, you did a work done, moving an object in this manner. This one is path B, you move the object in this manner. And this is path C, you move the object in this manner. If I compare the useful work done, which one will have a greater useful work done? Is it A, B, or C? Which one is having a greater useful work done? Is it A, B, or C? When I compare the useful work done. Actually, the correct answer for this one is they all have the same work done. The work done by the useful work done. Even if there was another option, like example, there was D also. And when I compare the work done will be same. The work done does not depends on the route or the path we follow. So A, B, C, or D, because our final positions are same and our original position is also same. So it is irrespective of how it is done, because whenever we calculate a work, what is the formula to calculate a work? Work is force multiplied by distance. That's a formula. So if I know the weight of this object and I know what height, the vertical displacement I covered, so weight multiplied by height, because the weight is a force, multiplied by the distance I move, vertical height is there. So weight multiplied by height. So for all these, I will use the same formula. So I will get the same result. So idea is that the work done does not depends on the route or the path we follow. It is irrespective of the path you follow. Work done depends on your starting position and the final position. Is it clear? Anyone having a doubt or a question about the concept of work till now? Another example. So work done does not depends on the path. It only depends on your starting position and the final position. Say there is an object which is on the ground You move the object and return back to the same place. What is the work done around a closed path? What is the work done here? Around a closed path. So in physics, work done around a closed path is zero. Because if you want to calculate a work, when you're calculating a work, it's a force multiplied by displacement. So you are applying a force, but what is the displacement in this example? If you're starting in the final positions are same, it means the displacement is zero. And when the displacement is zero, it means the work done will also be zero. There is no work done around a closed path. The useful work done is zero. There is a wasted work done, like energy is there, wasted, but the useful work done is zero. Same way, say a satellite is there, which is orbiting the Earth at a distance d from the center. The satellite is moving in a circular path. The gravitational force of the Earth is pulling the satellite. And the satellite is moving in a circular path at a constant radius. So if I want to calculate a work here, work is force multiplied by distance. So what is the work done by the Earth to move this satellite in a circular path? Because the satellite is moving around the Earth. So what is the displacement here? Like the change, there is no change. It remains same height above the Earth. So the displacement is zero. So if the displacement is zero, what about the work done? The work done by the gravitational force is also zero. So if the object does not change the relative position, it means the displacement is zero. Is it clear, this example? Is it clear? So on inclined surface, if I compare the work done, say a person at position A is having a weight of 70 kilogram and he climbs the mountain and reach the top. Another identical person, like of the same mass, which is 70 kilogram, and he also climbs the mountain and reach the top. If I compare the work done, which person did greater useful work done, A or B? Or if I compare the work done by A and B, two objects, two person have the same mass, reach the same height. If I compare the useful work done, so if I compare the useful work done, because I'm starting with the same from the same level and I reach the same height, so what about the work done? The work done by A and the work done by B will be same. As I mentioned, the work done does not depends on the route or the path you follow. It depends on your starting position because both are starting from the same level on the ground and both reach the same height. And because they have the same weights as the mass is same, so the weight will also be same. So when I calculate a work done by these climbers, so the work will be weight of these climbers multiplied by height. So they reach the same level, height, and they have the same weight. So that's why I will get the same work done. So work done does not depends on the route or the path it's followed. You can also calculate a work done on an inclined surface by using the components of the weight. Say an object is there at position A and you move the object to the top, position B. The height which changes, example H, and the distance which is moved, example D. And we want to calculate a work. What about the force a person is applied to move up? Yeah, I will compare that as well. I'm coming to that point, like how to work out that. So example, at this position, the force which is acting, like example, normal contact is there, but weight will act downward. And this weight will have the two components. One of the component which is with an angle. So one of the component which is with an angle, that is written as cosine. So this will be W cosine theta. And there will be another component of the weight which is opposite to the angle. That is W sine theta. So if I want to calculate a work here, so if I'm using this distance D, so which component I should use? I should use W sine theta. So if I want to calculate a work, it will be W sine theta times D. That is one way of calculating a work. If I want to use the height, then which component, like what is the force which is parallel to the height? So weight is the force which is parallel to the height. So when I calculate a work here, so in that case, the work will be equals to W multiplied by weight multiplied by height. So you can calculate a work done by these two ways. You can calculate a work done with taking a W sine theta into D, because the W sine theta is parallel to D, or you can calculate a work by using a product of weight into height. And whenever you solve this question, you will get the same result. Because as I mentioned, work done does not depend on the route or the path we follow. And one thing, our assumption is that there is no loss of energy, and there is no loss of energy. All the energy is used to do the work. If there is a loss of energy, then definitely when you calculate a work by weight into height and W sine theta into D, you will get a different result. Is it clear, this example? Any doubt in this? Any question or a doubt? What if we use a sine component of a W and D as a work? Yeah, we will use a sine component. So W sine, and the distance which is moved is D. So W sine into D, when we multiply, we will get, for example, say we got 30 joules, example. So when you use a weight into height, you will also get the 30 joules. So as I mentioned, it depends on which distance you are using and the component of the weight, you will get the same result. So work done does not depend on the route or the path we follow. Now, the same example of the climbers. So two climbers start from the same level. This is steeper, like the theta 1 is there. And this one is theta 2, which is smaller. The distance here moved is D1 example. And the distance which is moved here is D2. So if I want to compare the work done by climber, the weight of the first climber is say W1. And weight of the second climber is W2. I want to calculate a work done. So if I want to calculate a work done, and what if I don't have the height? So if I want to work done by climber A and work done by climber B. So work done by climber A, as we know, work is a product of force and distance. So I will take force, which is W sine theta 1 into distance D1. If I want to calculate the work done by B, So work will be the product of force and distance. So force is W sine theta 2 and the distance is d2. Remember, the value of the sine theta increases if the value of the theta increases. So if the value of theta increases, the value of sine theta will also increase. So what actually happened for A, and when we solve, we'll get the same answer for A and B. But how we'll get the same answer? Because the theta 1 is greater than theta 2. So if the theta 1 is greater, the value of the sine theta will be higher. And the d1 is shorter. Same thing, when we take theta 2, the value of the sine theta, because theta 2 is smaller, the value of the sine theta is smaller, but as you can see, the value of a d2, the length which is covered is greater. So but the product of sine theta 1 into d1 and the product of sine theta 2 into d2, that will give us the same result. That's why the work done by A is same as the work done by B, and we assume that both climbers have the same weights. Is it clear, this concept about how to calculate a work? Anyone having a doubt or a question till this point? So work done is independent of the route or the path we follow. And if I was having the height, what if I was having the height and the two climbers are having a weight W? So I want to calculate a work in that case. So how will calculate a work? In that case, it will be the force, the weight multiplied by the height. And I'll get the same result. So work done does not depend on the route or the path we follow. Then whenever there is a work done, it either stored as an energy in the object or it transferred to an object as an energy. Different forms of energies are there. The two main forms of energy which you have to learn is the kinetic energy. Whenever a work is done to move an object, we call that as a object is possessing a kinetic energy. Say there's an object and you have to learn a short derivation of this kinetic energy. Example, there is an object which is initially at rest, not moving. It experiences a force F, a constant force F is there, resultant force F. So what will happen? This object will accelerate and it has an acceleration of A. So a force F causes an acceleration of A and the object moves to new position D. The final velocity at which the object is moving, so that velocity, example V, like the velocity at a distance D, that velocity is V. So if I use the equation of the motion, I can say that 2as equal V square minus U square. That's the equation of the motion. It is only applicable when the object is accelerating. Or I can also say, if I substitute, so 2, acceleration is A, the distance move is D. The velocity, final velocity is V square and initial velocity is 0. So when I simplify this, it will be 2AD is equals to V square. Or I can also say that the D is equals to V square over 2A. So the distance moved by this object is actually V square over 2A. Now I want to calculate a work done because whenever object is moving, the work done is equals to kinetic energy. So if I want to calculate a work done, I need the force and I need the distance. So the force F is there and we know the resultant force F is equals to MA. So in place of F, we can write MA. What about the distance moved by this object? We just derived the distance moved by this object is v square over 2a. So if I put v square over 2a, when I simplify this work, a will cancel with a. So what I'm left with 1 by 2 mv square. And this 1 by 2 mv square, because whenever work is done to move an object, what we call that work done, we call that as a kinetic energy. That's why the formula for the kinetic energy is half mv square. So whenever you calculate the kinetic energy, you get 1 by 2 mv square. So for an object which starts from rest, reach a velocity v with a constant acceleration of a, the distance covered will be v square over 2a, and the work is the force into distance. And F is equals to ma, and the distance is v square over 2a. So when we simplify, we got the formula for the kinetic energy. So work done to move an object is always equals to kinetic energy. If an object is moving at a constant speed, it means it has a constant work done or constant kinetic energy it possesses. Moving objects always have a kinetic energy. What actually this work is showing? This is showing the change in kinetic energy. So if I want a kinetic energy at this point, it will be half mv square, but the speed is 0, so the kinetic energy is 0. Kinetic energy at this point will be half mv square. I'll get the kinetic energy and I'll take a difference to know how much the kinetic energy has changed. So half mv square is actually showing the kinetic energy at this specific point. When I use the formula half mv square, I will get the kinetic energy at this specific point. So if an object is moving at a constant speed, it means its kinetic energy is not changing. Is it clear, this example? That's how we work out the formula for kinetic energy, which is half mv square. Same thing, if there's an object of weight W and you move this object to a certain level, so weight of an object is W, which is acting downward. And we lift this object to a certain height. And you want to calculate a work here. So work is force into distance. What is the force? So the force is the weight and the distance is the height. Weight is mass into gravity and the height is h. So whenever a work is done to move or lift an object, so work done is known as, like it will be stored in the object as a GPE or gravitational potential energy. So when we lift an object, the work done is mgh, which is the weight into height or mass gravity into height. And we call that as a stored energy as a gravitational potential. But when object is moving, it will have a kinetic energy. And if object is changing the height and moving, it possesses both gravitational potential as well as the kinetic energy. These are the learning objectives. So about the work done, just I explained that idea about the work done. So example, when calculating a work done, that is the force and the displacement, and we always take the parallel one. So say a child starts from a rest here and he slides on the inclined surface. So if we want to calculate a work, we have a distance 5 is there, and we have like a length of the inclined surface that is 5, and the distance is, the height is 3 meters. So if I want to calculate, and this one is 4 meters. So if I want to calculate a work is force multiplied by the displacement, which is parallel to the force. So the force which is given is the weight here, which is 250. So what component I will use? I will use 3 meters. So 250 times 3, what we'll get? We'll get 750 joules. If I was dividing the weight into the component, so this angle theta was here. This is the weight. So this is a component which is with an angle W cosine. And this one will be the component that is W sine. So if I have a W sine theta, like I was having an angle of the inclined surface, in that case, if I want to calculate a work done, I will use W sine theta multiplied by 5 because the 5 is parallel to W sine theta. So whenever you calculate a work, it's always the force multiplied by the component which is parallel. So example, a man wheeling a barrow, he's applying a force of 540 newtons at an angle of 75 and he moved this 30 meters. So this force is having the component, one is with an angle, so this will be F means 540 cosine 75 and another one is 540 sine 75. So which component I should use? I will use 540 cosine 75 and multiplied by the distance moved. So we'll get this 4,200 joules of work done. So the idea remains the same that whenever we are calculating a work, we always take the component which is parallel. And whenever work is done, we have different forms of energy, kinetic. When we are able to do a work to move an object to a certain height, it will be a kinetic energy. I'll share another link and we'll continue this topic about the work and the power.